All right, here is example 1 from class 16. Now this is a really long example because I want to go ahead and work through this problem in 2 different ways. And I'll try not to belabor it too much, but it is a good problem to fully show different methods to solve, right? So we could either do the vector math or the acceleration diagram. So I will go through both of them, but I will usually default back to the velocity diagram, the 3 diagram method. Now, I had mentioned that every time we do an acceleration analysis, we need to do a velocity analysis, but we already did this problem with velocity analysis in several different ways. And our purpose in doing it was to find omega. So omega ABC is 0.4138 radians per second, and that is clockwise. So as a vector, it is negative 0.4138 let's put K, right? Because it's coming out of the board. It's negative because it is clockwise, right? And if we wanted to use vector math to get this, we're going to have to write out the acceleration equation. So, first off, we need to define what we know. We're told that the acceleration of B is upwards. That means it's decelerating, right? Actually, we say it's decelerating then, and then we know that it happens to be upwards. The velocity is downwards. The acceleration is upwards because it is accelerating. So, we also know that A is going to be constrained to move horizontally. So we can write out some of the acceleration equations, at least the format of them. So we know that acceleration of A is going to be equal to the acceleration of A in the x direction entirely, I plus 0j. The acceleration of B is given, and that's going to be 0 in the I direction, and it's going to be a positive 0.5 in the j direction. And I'll leave off, but these are feet per second squared. It should be the units for these. All right. So I'm also going to need the position vector of A with respect to B. So that's going to be A with respect to B is going to be so we're starting at B and we're looking at A, so that's actually negative L AB, and then we're going to have that's going to be the cosine, because that's theta right there, so it's going to be the cosine of theta I, and then A is above B, so that's going to be plus LAB sine of theta J, right? And if we plug some numbers into the thing, that would just be negative 3.625 I plus 1.690 J, right? That might be something worth keeping. And the equation that is going to define the motion of A is the acceleration of A is equal to the acceleration of B plus alpha K, right? That's the acceleration, angular acceleration of ABC. I could write that underneath the thing if I want to, ABC. Really, because there's only one piece right there. You don't necessarily need to give these subscripts. That's crossed with the relative position of A with respect to B vector that we've just written up above, and minus omega, and that's ABC actually, squared, that omega squared, and RA with respect to B, that position vector. So if you write this out long ways and fill all the blanks in here, we say that A X I right there, and I'll leave off the J part, or I guess I'll put it in there. It's really gonna be tough to fit this stuff inside here. Is going to be equal to, now I go to B right here, 0I plus 0.5J, and then we go plus alpha, and we don't know what alpha is, so let's just keep that as a term. Alpha, I'm not going to, just to save space, no ABC onto that, that's what I mean, onto the thing. And it's going to be times, let's see, did I do this right way? Yeah, I guess I go times this weird way I put parentheses and parentheses, 6.25 right there, K crossed with I, right? Because I took this guy and I applied it to this first term over here, right here. And then it's going to be plus alpha times my 1.690, and that's K crossed with J right here. And then I'm going to have, now I have minus right here. So I go minus my omega squared, and I know omega is 0.4138 squared times my negative 3.625 I, right? I'm not going to be able to fit everything in there, unfortunately. And then minus 0.4138 squared times 1.690J. Okay, so I take a look at this, I cross K with I, and we know that that's going to come up with a positive J, but if we cross K with J, we end up with a negative I. We group a whole bunch of terms right here, or we could go ahead and just take a look at the I direction, but I think it's easier to take a look at the J direction first. We're going to say that 0 is going to be equal to 0.5, and then plus my alpha. Actually, I could just go ahead and make that negative right there because of that negative right there. So negative alpha 3.625 right here. And J is getting in my way, so I'll repeat him up here. There you go. He's up there. And we have one last J over here, which is also going to be a minus 0. Oh, by the way, I did actually, this was a minus right here, but it was a minus inside there. By the way, that minus was inside. So we didn't have to worry about it because it got squared. But if we were going to be correct, that minus didn't show up. There you go. That minus what needed to be right inside there. I guess am I keeping him in there? I guess I didn't work out what the number was. 4138 squared times my 1.690 right there. And from that, we're able to find that alpha is equal to 0.05808. That's going to be radians per second squared, and it's positive. Therefore, we know that alpha is actually in that direction, even though we had previously found that omega was in that direction. But it kind of makes sense that because we had that deceleration at B, that it might be in that direction. And we could also, from this, if we wanted to continue and get what I was going to be, we use I, and then what we end up finding is that A in the X direction, which is in the entirety of the X direction, would be 0 right there, and then right here it would be, it would have a positive component, no, actually it would be negative right there, right? So that negative right there, and we just got alpha 0.05808 right there times my 1.690, and then this one is this is actually going to be positive right here because that guy is negative and that's negative right here. So we're going to actually add that into there, which is an interesting issue that takes place. Let me double check. Actually, I didn't solve this. Oh yeah, I did. Okay, yeah, no, never mind. Yeah, I solved it. So that's then they ended up being positive, even though that's a negative inside that square. It doesn't matter; it goes away, and we end up with 3.625. And what we find that ends up being 0.5226, and these are feet per second squared. And because it's positive, you know that it's going to the right. That it still is accelerating to the right as part of that, which is an interesting outcome. Let me double check on all of that. I think that's true. I want to double check on those values right there. Yeah, that's probably that's probably true because this one is so small and that was positive. So that's fine. But the thing we were asked for as part of this was the acceleration of c. So we need to do all of this over again, which, I'm almost kind of wishing that I hadn't asked the question that way, but I did. So we'll once again use a b as the reference, excuse me. So we will write this thing out a long ways, and that's going to be plus alpha k, right, crossed with r c with respect to a, with respect to b, we're using b because we know b. It's a nice thing to use. And then minus omega squared r c with respect to b. We haven't written yet. We need, in a similar way that we did up here, we need to write this out. So we need to write our position vector r c with respect to b. That's going to be it's going to be positive, and it's going to be L on the IL BC. And again, I believe that's going to be the cosine. Did I write that out anywhere? Interesting. No, I did right here. Yep. LBC cosine of theta I, and now it's going downwards. C is downwards from B, so minus LBC sine of theta J. And we put some values in there, and we're going to end up with a positive 5.438 I and a negative 2.536 J. Okay, I need more space, so we go to the next page. So, by the way, we might have wanted to write out our alpha as being as a vector. No, we're okay. We know it's positive. We know it's positive right here because it's counterclockwise. All right, so the way that I want to treat the acceleration of c, we'll treat it generically, right, in terms of the vector. Right there. So there's just have components in front of the I and the J, components that we don't know. And we could draw, if we were to draw them on there, they would look like this right here, to be shown, right? We draw them as positive because we don't know what the answer is yet. So we take the acceleration of c and xi plus the acceleration of c, y, and that's times j. And that's going to be equal to the acceleration of b, which was 0, I, plus 0.5 j. And then we add to it the angular acceleration, which we just found, of 0.05808, and multiplied by the position vector right there, 5.438, right? And that's going to be the first part, that's k dotted with I right here, and then I have enough room, so I'm going to come down over to here. We're going to go minus, well, actually probably should go right here, 0.05808 times minus 2.536, right? And that's k crossed with j right there. And then we have the next terms are minus, and we have a minus 0.4138 squared, right? So that's going to get rid of the minus sign inside the parentheses, but not outside. Why did I make a minus up there? Because I was saying minus. That's squared. Times the first part of the position vector, which is 5.438, and that's I. And then lastly, minus 0.4138 squared times a minus 2.536, and that's going to be j. All right. And so there's a lot of stuff going on here. It's a pain, right? Let's double check. We know that this is going to be a positive j. That's going to be a minus I after we cross them. So we can collect terms, and in the I direction, let's see, it'll go down a little bit further so we can try to write it across. I direction, we have AC x is equal to 0. I guess I'll write out the whole thing, whatever. Minus 0.05808. I think I got that right. But you notice it's minus, so that's going to be plus right there, our 2.536. Okay, and then a minus. We could keep that minus inside the parentheses. It doesn't really matter because it's going to get squared. And then 5.438 right there. So if we do that, what we end up finding is we have a negative 0.7839 feet per second squared. In the j direction right here, we have ACY is equal to 0.5 and plus our 0.05808 times our 5.438, all right? And then for the j part of it here is we have a minus, so that's going to be a plus. Is that true? Yes, I think so. And I'm just keeping the minus inside the parentheses just to be consistent, but it goes away, and so it's 2.536, and what we get is a positive 1.250 feet per second squared. So the acceleration of c is negative 0.7839 I plus 1.250 j feet per second squared. And this is just part one of this example. I'm going to continue it onto another video because this one is already pretty long. But we'll see what we use when we do the 3-diagram method. So this is using vector math, just continuing with the more consistent, methodical vector math part of the thing. I prefer the 3-diagram method. So we'll talk to you soon, and I'll discard all this.